250,000 what you paid.
So please write 14.2 or 14.3 above your work so that we can locate this section.
For 14.3, I didn't evaluate the integrals. Like that part was easier than finding the limits. Do you mind if I just show how I found the limits?
No, not at all, because I know that your integrals are calculated in relation, so it's... Let's see, did you write 14? This is 14.3, and that first work is 14.2, so here we go. We're nicely done on 9. Oh, you definitely know what you're doing. 9 and 10 are perfect. Is this the point x equals 8?
Yes, yes that is.
Okay. And we have a winner here also, nicely done on 15. So 14.3, you want to just show this. So Stuart has some nice work up there. Okay, quit checking the one.
Oh, it's just for, this is, here. Oh, sorry, Stuart.
Stuart, you okay? Stuart?
No, I'm good.
What?
Stressed out when it.
No, I just have an irritated eye. It's not that at all. But you've done this integral before, that sine squared becomes sine theta cosine theta. Be sure of that integral. I thought it would be a 2 theta. But did you just make that up, or did you check it out or something?
No, because,
Integral sine squared?
yes, that is a 2 theta. Is it the 2 from the?
No, not the 2. What's it, do sine
This is,
problem.
this is,
No, just, can you do integral sine squared for me? Sine squared theta d theta. Can you do that integral for me?
and that equals, the 2 comes down, and the sign is, or actually it's 3, and then it's a cubed.
No, it's not. Mm-mm. Can't do it that way.
The 3 comes
I'm
out.
not gonna move you down.
On the side? I know, it becomes a cube. Because this sine squared is sine cosine, right?
No,
Yeah.
not sine cosine.
That's a little doohickey in my other calculus book.
Okay, if you can find it, then I'll believe it. But I'm not gonna believe it.
Okay.
No. The standard way to do sine squared is 1 plus cos 2 theta, a half angle. Cos 2 theta equals cosine squared theta minus sine squared theta equals 1 minus 2 sine squared theta. So, sine squared theta equals 1 minus cos 2 theta over 2. This is the only way I know to do sine
Yeah,
squared theta.
that's a formula.
Okay, well then when you integrate this, you get sine of 2 theta. This is a formula. So then you have to integrate that. Integral sine squared theta d theta equals the integral of 1/2 d theta minus the integral of cosine 2 theta d theta. Okay? So this is equal to 1/2 theta a to b minus sine 2 theta a to b. So this is what I get, so don't this is the only answer I know to it. Because those other ways, you're violating rules. Because this is not u squared du, because this is not the derivative of that. This is the derivative of this. You're absolutely right. The integral of u squared du is u cubed. But this and that have to be related. This has to be the differential of that.
So the sign is not
So what you've got is,
associated to it.
No, it's
just
not.
because it's d theta.
it's not anywhere near that simple. It's a hard integral. So why don't you just look it up? I mean, it's a standard integral. Look up the integral of sine squared and use it from the table.
Yeah, here it is. 1 minus cosine alpha over 2.
Cosine 2 alpha.
Sine squared
Of alpha over 2.
of alpha over 2.
Right, so one is twice the other. So one is twice the other, agreed?
Yes.
If you got alpha over 2, you got alpha. If you've got theta, you've got 2 theta. So you've done that in earlier classes too, and I just let it go. But let's take a look. Well, you did one perfectly, so there's no sense saying it's not right. Could not be better. So, beautiful, beautiful job. No question about it. Now, the next one's number 3, agreed? So let's see how that comes down. Well, you got the a cubed correctly, and instead of 2/12, we would left 4/9, but that's only arithmetic. Yeah, no, you did all the calculus perfectly, so don't worry about it. It's all right. So you did 2 out of 2, very, very well. So now you look at number 6. And Stuart's looking at some kind of Cartoroid. But it's the integral of cosine 4. You've got the integral sign. You still have one-way integral to do.
Where?
Here. See, you still have, after you substitute this, you still have to do the d theta integral. Oh, you're doing it now, I'm sorry, apologize, okay. So no, you did great, AJ, you have nothing to worry about. You're doing everything just right on. So this is 14.3, number 11. Well, they look just like your pictures in 12.2. So,
Oh, I messed up 12.
wait a minute, let me see where you erase. 1 plus cos theta to 1, pi over 2, 3 pi over 2. Yeah, maybe they just took a different setting. So you want to have this shaded region. So the R integral is inside, and the R is specified. Looks like they have to do 2 regions here. Oh yeah, the R goes from 1 plus cos theta to 1, because this is an R vector, right? And this is the point that matters.
Yes.
So it goes from 1 plus cos theta to 1, the typical R vector, as a function of theta. This is the starting place, so this is the only R that matters right here.
It starts up at the top.
I haven't done
Oh, no,
anything
an
from
arbitrary
14.2
R vector.
besides 1, 3, and 6.
An arbitrary R vector.
You go to the wrong,
where's
it's supposed to be 14.2.
Well, one is a circle. This is a circle, R equals one.
How do we get that mixed up?
So all the R vectors in that circle, they
It's
turn.
that test. Spent
Okay.
so much time doing the polar coordinates thing.
It was horrible.
So the upper limit's a one.
So this right?
No. I'm
And-
still trying to figure out how my integral is different.
Which
Yeah.
one?
Okay, you got it now.
I had to
Okay, good.
erase this
That's it.
because this becomes this.
Okay, so let's
And
immortalize
then when you
this stuff.
take the integral of this, right, because this has to be the integral of
Mhm.
that, then
Those
this
are
becomes
impressive.
pi over, or
Excuse
beta
me,
over
guys,
two.
can I twist your cord?
Yeah.
Okay. Well, now we have a nice
And
video
this
on
becomes
this.
one, but then this becomes sine squared.
AJ stuff here, which is
Right.
excellent.
And then this still becomes, because there's still a two over here.
Jake
Well,
stuff here.
sine squared over 2, because that 2 needs to disappear.
The problems here, all of which are exquisite.
Yes.
Okay. Stewart over here. Two problems.
He said my integral was wrong, so the sine squared is one minus.
Here you said this interval
One minus
wrong?
cosine. This one right here was wrong. He said it was one minus cosine. Two theta. And it would be over 4.
1 minus cosine 2 theta over 4.
Or well, over 4 because this is over 2.
Two?
That was this 2. But this is
The
over
2
2.
has,
Right, because that 2's already there, and then that 2.
2 always
That's
has,
just in Calc 1. Somebody forgot.
2 always has theta.
I'd have to look it up as well.
When you take the derivative, that 2 must come out something. See, that was the
Well,
whole-
then this becomes, yeah, this is actually this.
Then maybe it goes to a 4. You have to put a 2 there.
It's over
Yeah, it goes to
4.
1/4. The two,
Yeah.
it is a 4, I'm
It's a
wrong.
4,
It's a 4. Yeah.
Maybe there's a trigonometric identity.
which is what I had before, but
What you have?
Did you have 2
Maybe
theta though? Yeah. It's a 4.
it's, well, then this becomes a theta over here, right? Because this, you have to take the integral of this, minus, and then 2 plus sine 2 theta
Mm-hmm.
over 4.
Yes. Bingo.
So that was this, right?
So compare timing.
So this theta, this becomes, oh, that's why I had a 3, because that becomes 2 theta over 4. And it became 3 theta.
So this is 14.3
Yeah.
number.
This was originally a theta over 2.
Yeah, I don't dispute that, I just
So,
want to see this.
If that was a theta over 2, this became 2 theta over 4, to add it to that theta. And it became 3 theta. 3 theta plus sine squared theta
Sounds,
plus 2 sine.
good,
2
okay,
theta.
now go between your limits and see what you get.
Right.
Your limits and pi over
Which
q
is
would
what I
be
had
pi over
originally.
q. Well, you didn't have a 2 theta.
No, yeah, you're right, I didn't, I had a
That
sine
was my
cosine.
objection, that you
Oh,
didn't have
okay.
a 2 theta.
Should be
It's
fine.
sine
Okay, so
theta,
it's
cosine
this.
theta.
2 sine squared
And I
theta.
need, huh?
2 sine squared theta.
2
He
sine
wants-
2
He wants a
theta.
2 here.
Because over there it's divided by 2, and over here it's divided by 4.
That's obsolete.
Oh, okay.
Oh, no, it's 2. You're right. 2, you're right.
Good job. Okay, now between your limits,
And then between my limits is 3 pi over 2.
And the top?
First one's
3 pi over 8
Times 3.
times 9.
Okay, keep going. Sine of pi over 2 is a 1, so that's easy. So it's just a 1.
So 2
So it's
times 2,
times 2, right? Okay.
and that's over 4,
And sine of
which is
pi,
1/2.
sine of pi is a 0, so that's why it drops out. Okay.
And then this would be minus pi over 2. So 3 pi over 8
Just
plus
gonna get the right answer.
0. I don't know without my calculator, I can't remember. And then sine
Minus
of
1.
pi over 2 is minus 1, so minus 2.
Minus 2 over 4. Look at this, you can get the right answer.
4.
All right, keep going. So 6 pi
So
over,
these
oh my
cancel,
God, she got it.
And then
She's
6
got it.
pi over 8,
That's awesome.
which is
3 pi over
3
4.
pi over 2
3 pi over 4.
over 4.
Yeah, nice work. Awesome. Hard problem nailed. Okay.
Figured out why it's.
I thought you said that was the easy one. I wonder what the hard ones are like.
Figured out why it's easier to proofread someone else's work.
Is this my own handwriting?
Because I have no idea what's going on, so I have to look at every term and be like, what is happening here?
Oh, yeah.
Okay, we got to go to new material now. We got 30 minutes left and get the new sections out. Okay, I've got some interesting announcements for everybody.
You're going to throw our test tube away?
They're
Perfect.
giving us all A pluses.
I'll take an A minus.
I will take a B.
My school doesn't do pluses or minuses.
I'll take a B.
Well, way to aim high.
If I get a 99 or I get an 89.9, I get the same.
Oh, Saki, no. Monica.
Maybe that is aiming high.
Don't forget your calculators.
It could be.
There's a calculator in the back there.
That's mine.
Yeah, Saturday night, my husband's like, I'll go buy you a graphing calculator. I'm like, forget it. It's over.
I've got 3 weeks left of school.
Bite your tongue too.
Okay, so announcement time.
This is my one for kids.
Hmm?
My one for kids.
It'll be outdated by that point.
Mine's 10 years old. It's still great.
It's typically the same.
So the Friday of next week, we'll have a final exam, which is going to be drawn from these homework problems that you're so carefully getting good copy for. So we have to address the subject matter of the next 5 classes, 3 classes this week and 2 classes next week, Monday and Wednesday. And I'm carefully looking at the remaining material. Then our very next section is 14.4. It starts on page 1026. 14.4, 1026. And the topic of this section is surface area and parametric surfaces. We're going to do the surface area part. We're going to skip the parametric surfaces. So we're only taking the very first topic in this section. And this very first topic is called surface area for surfaces of the form z equals function of x and y. These are very simple to do. In fact, I'll show you quickly how to do them. If you have a canopy that is above some xy footprint, then what we've been focusing on now so far is the volume that's under that canopy. Does everyone understand what the word canopy means? It's like a parachute. It's a curved surface in space. AJ, you familiar with canopy? It's a canopy is over a porch. It's the roof of a porch. It's a curved roof. This is a canopy over my head, see? It's a canopy, it's a curved surface. So you have a canopy or a curved surface that has a shadow or a footprint in the XY plane. And up until now, we've been answering the question, what is the volume under that canopy? Now we're going to ask the question, what is the area, surface area? Because it's a curved surface, but it's still a surface, agreed? So it has some number of square feet in it, or square units. So you have to ask the question, if I want to paint this canopy, how much paint do I have to buy? So what is its surface area if you cover it, so add it up? Now it's a little hard to do because it's a curved surface. So it's not just length times width like it was a plane surface. It's a curved surface in space, so the area of it is a little bit harder. But we answer that by a parallel development. You know that if in 2 dimensions you have a curved line, and you want to know the length of that line between 2 points, A and B, then you know that the length of that line is the integral from A to B of the square root of 1 plus dy dx squared times dx. How many have seen that integral before? So that's how you find the length along a line between 2 points A and B. Now the equation for this surface is some z of f and x and y. That is the equation of the surface. It gives the z value above the xy plane. And the area of the surface, S, is then just the integral this is S, it's the area, it's not an integral sign. The integral over the footprint R, this is the footprint, the region R, of the square root of dz, these are partials now, dz dx squared plus dz dy squared plus 1 times dx dy. So you see the similarity between going from the length of a line in 1 dimension to the amount of surface area. Since surface is actually a 2-dimensional item, even though it's curved, it's still 2-dimensional. And then the integral also involves the square root. It also involves derivative squared. It also has a plus 1 on it, which comes about in a very similar way. And it's integrated over the region. Only now the region involves a double integration, and the region in the case of a line involves just a single integration. So the basic equation that you use to find surface area is dz dx squared plus dz dy squared plus 1 and integrated over the region. Okay? Now the derivation of this is not hard, and I'll do it in the last 5 minutes if we have time to come back to it. But this is the only item that we're taking from this section. So let's look at page 1026. And in the drawings, we see we have a canopy, z equals f of x, which exists over its shadow in the xy plane, which is known as its footprint or region R. And then you can make a 2-dimensional graph of the region R, which helps you to do things like find limits. Now, if you want to establish the equation that we have it on the board, then what you do is take the part of the canopy that's directly above your little square unit area in the footprint, and that part of the canopy will have 4 points on it that are the elevated points of the rectangle in the footprint. These 4 points will indicate 2 edges, and what you do is draw the tangent plane to the canopy at that point. You draw the tangent plane. And what you do is you estimate that the area of the canopy is the area of that little tangent plane that you drew. And that's the same type of estimation that you made in one dimension when you said that the length along the line was the same as the length of a tangent along the line. And the tangent was dy dx, so that's why dy dx came. Now, the area of a parallelogram, because you see this rectangle in the xy plane, when you project it up, is going to come into an arbitrarily tilted canopy at a slant. So it's going to appear on the canopy as a parallelogram, even though it's a rectangle. Because when you take a shadow of a rectangle from different angles, it often appears as a parallelogram. So in general, its presence on the canopy will be a parallelogram, and a parallelogram has its area as a cross product of 2 vectors along its side. We established this as a cross product. One use of the cross product was to give the area of a parallelogram. And these 2 vectors in linear form along the 2 edges are given at the top of 1023. A vector along one side of the parallelogram, it starts at x equals 0, and it changes by an amount delta x, and the z value changes, as you would expect it would change, by dz dx delta x. And the other edge of the parallelogram has a 0x value. It propagates in the y direction, an amount delta y, and it raises upwards dz dy delta y2. So these 2 vectors are along the edges of the parallelogram. So if you cross them, then you get the area of the parallelogram. And when you cross them, then you get that S is equal to the Riemann sum, dz dx squared plus dz dy squared plus 1, all square rooted. And then when you pass to the limit of the Riemann sum to the integral, then you have the integral expression that we have on the board. So the way to use this is extremely simple. You have a function z. You take its 2 derivatives. You substitute them. You integrate with dy. You integrate with dx. And all we're doing is taking very simple integrals that have a box on the base. I may have assigned some that actually have a equation on the base. That's okay if we did. Now, the topic that we're going to avoid in this section is called parametric representation of surfaces. I've decided that there are other topics that are much more fruitful to include in the same time that we would be spending on it. So we go now forward to the next section, which introduces absolutely nothing new to you, and it's on page 1039. And it's called triple integrals. Okay? Now, a triple integral is when you integrate over all 3 dimensions, dx, dy, dz. So you start with a little region. Suppose you want to have the region of a sphere. Then you start with a little cube inside. And this cube is known as dv. It's equal to dx, dy, dz. And the integral of the sphere is just the integral of dv. So it's equal to the integral of dx, dy, dz. Now, this would probably be more easily be done in spherical coordinates because it's a sphere. But the basic way that you do a three-dimensional volume integral is you have a little cube, dv, whereas in 2 dimensions, we had a little area, dA equals dx dy. And we integrated our little dA over the region that we wanted to know the area of. Here, inside of an arbitrarily shaped volume, you have a little cube, dx dy dz. And you integrate up the cube in all 3 directions till you come to the boundaries. The end of your integral will be, indeed, the volume. So the typical case would be that we have a box, which we take a little integral of the area, dx dy dz. And we integrate it up from A, B, C, from 0 to A, from 0 to B, and from 0 to C. And we get the volume of a box is length times width times height. Now, these are called integrating up the volume where the limits of integration are not curved. You're just integrating up to a rectangular box section for your limits. That's the simplest one, and that's the one we're going to devote our attention to. So the definition of a triple integral is the integral over all 3 dimensions. Now, all we're going to do is integrate over boxes. So we're going to look at the bottom of 1040. If A is in this theorem at the bottom of page 1040, if A ranges from A to B, Y ranges from C to D, and Z ranges from K to L, then we integrate our 3 dimensions and plug in our limits, and we have our answer. So what I've done right now, so far, is just integrate up dV by itself, which would give me the volume of the region, the volume of the region that we want to have. Now, besides just integrating up dV, you can integrate up some property of the space. So here you have a property of the space that depends on all 3 variables. And I can give you a very classic example. Suppose I want to integrate up the amount of air that's in this room. Well, what I do in the room is I take a little dV, a little cubical region. Now, the amount of air that's in that region, dm, the amount of air, the mass of air, is the density times the volume. Mass is density times volume. That's what density means. So if I know the equation for the density of air in this room, I can calculate the mass of the air in the room. It's the integral of dm, which is the integral of rho dv, which is the integral of rho x, y, z, dx, dy, dz. So this is a typical example of a triple integral of a function evaluated over a volume, where the function has different volumes, different values at different volumes in the function, in the space. So another example, might be the number of people in the skyscraper. Right? So you have a function for the number of people in all three dimensions in the skyscraper. Now, the function is there's going to be more people on the lower floors than there are in the upper floors. There's going to be more people out by the windows than there are near the middle of the skyscraper. So you have some function that gives you the number of people at different points, X, Y, and Z, inside the skyscraper. So you take that function of people density and you integrate it over the three boundaries of the skyscraper, and it'll give you the number of people that are present in the skyscraper. So anything else that can be represented as something that varies in space, something that is different in space, and you can integrate up to get the total amount of that substance that's in the space, is the type of thing that we're doing here. So these problems are not challenging. The challenging problems we're skipping. So the types of problems that you're going to be doing are on page 1045. So you're looking at number 1 or 2, okay? And you agree that they're not scary. Now if you look at 6, 7, and 8, you see you are involving that the extent of one variable ends on a curve in terms of another variable. So you just do the same type of iteration that we've been doing in 2 dimensions. Nothing changes there. Okay. Now the reason that I chose to stop doing this section at that point, we go on to the next section, triple integrals and cylindrical and spherical coordinates. Now that's something that, oh no, I didn't choose to stop doing that. Let me go back a little bit. I chose to continue this on Wednesday night. So on 1041, we're going to evaluate triple integrals over more general regions, where we no longer have the baby boxes, where we're actually going to have regions that have curved surfaces and are generally. And this you will hate. So you can get a step up on it if you care to. And then we go to the next topic, 14.6, where we go from triple integrals in boxes, X, Y, Z space, to we do triple integrals in both cylindrical and spherical coordinates. This is important because most of the real life triple integrals that you do are going to be in spherical coordinates or cylindrical, because very little of nature is boxy. Nature likes spheres a lot more than nature likes boxes. Okay. So when we finish that, then we will come to our last section in this chapter, 14.7, which we're skipping. Yes, sir?
Are you covering 4 sections tonight?
No. No. I'm covering the stuff that I alluded to. I'm covering 14.4, the first topic, surface areas. Stop. I'm covering 14.5, the first 3 topics. Stop. And then on Wednesday, I'm going to finish 14.5 and add 14.6. That's what we're going to do Wednesday. Okay. Then we're done with chapter 14, intentionally and purposely. Because if you turn the page to chapter 15,
I thought you said we were doing 14.7.
no, skipping 14.7.
Oh, we're
I was
skipping.
about to say we were going to skip it when I thought a question there. 14.8, centers of gravity. Very good topic, but not as good as some of the stuff that we could do instead. So what we do is choose that some of the topics in vector calculus are much more significant than these sections that have been chosen to be skipped. So if you turn to the beginning of chapter 15, page 1085, then you will see some stuff that is going to make you feel that it was worthwhile to go through all of this pain. because you get to use what you've now learned in some very powerful situations. And if you turn the page to 1087, you see something called the gradient. Well, you already know what the gradient is because you paid your dues. And then on 1088, and we'll get to this probably this Friday, you're going to see why I chose to skip what I chose to skip, because we get into two new items that are exceedingly powerful and important, and the names of those items, just to look ahead, are divergence and curl. And if you want to, you can YouTube these and you'll get thousands of responses.
Sounds like a band.
Yes, divergence and curl are extremely powerful.
So we are doing 15. I thought you had said we were not doing 15.
That's before you guys just showed me how fast you were. And
It's
I have a week
those
left.
two. I'm not doing anything.
Me?
What do you mean? You just did that powerful problem with complete precision and correct
think
With
you-
answer.
I think
help of
you
the two
overestimate
smart
my
ones on the
ability.
left side of the room.
Well, they'll be here next week to help you
Check-
too.
Chapter 15 is like the bonus of calculus, right?
It is the bonus.
Pretty much
It
all
should
the
be bonus on the
applications.
test.
It will be bonus on the test, but there are no basic points on the test. All the tests on the points on the test are bonus points. So
Sweet, I already got 100.
I just
Doesn't
can't
have any
wait.
bonus
He has
points
a
you
math
get.
fetish. I think
see how
that's
many
all it
bonus
is.
points you get. Okay, now on
Pleases him to see a stroke.
1090, you see something called the del operator, which is something I very clearly introduced to you already. Okay, so
Multiplication.
you've been there, and at the bottom of the page you see the Laplacian, which I've also already introduced to you.
We
And
might have been
curl.
introduced, but him and I have gone our separate ways.
Well,
He Laplace that way, and I Laplace this way.
He has a restraining order. I
Okay.
can't do anything with
now
his operators.
15.2, a line integral. If we get time for it,
We don't have
We
that.
won't have time.
well, we're up to Monday now, and we've got nothing to do on Monday.
We have review for
You
Friday's
have what? I
final.
don't know that word. Okay.
Study.
So I found out something interesting. This book
Should be burned.
Maybe we should.
is covered in 3 semesters at Maryland. Huh?
The international mission for a reason.
3 semesters, and
So
you
are-
guys feel squeezed. I just found out, I checked MIT's schedule, they do this book in 2 semesters.
They're a
Yeah,
lot
but
smarter than
they're
the other
going
place.
to an engineering school specifically
They're
for
going to a
engineering.
16-week semester.
No, they're not yet there. Didn't have finish it faster and add new material.
Yeah.
So you guys, if we amped up the rate 50%, then I would listen to your screams, but look what we're doing here. We're leaving out huge chunks, skipping sections.
But there's a difference between an MIT student and us.
Yeah, it's called motivation.
It means not married, no kids.
No, they are. Okay, so we're out of here. So what I've done is allude to what we're going to do for the remaining 2 weeks.
Most MIT students who are doing this are probably studying their freshman or sophomore year.
Yes, they finished all this book in their freshman year.
Exactly.
They do.
Yeah.
Then they do differential equations and linear algebra in the second year.
I finished this book like sophomore year. I'm close.
I asked my husband to scan papers in for me so I can figure out how to get this test done, and he's just like, I don't know, I'm reading Japanese on your paper. Don't
That's
ask.
right, you guys do know the cryptic language of the priesthood now. Squiggly lines and cursive Ds, yeah?
Oh, yeah. One of the kids on my bus
And if
asked me
it's
how
not
hard
cursive
math
the right
got,
way,
and
I have to erase it and
stopped
rewrite
doing
it.
letters, they stopped doing letters. And then they got scared.
That's part of the reason why it takes me so long to do stuff.
Yeah, that's very good observation.
I'm anal.
Very good observation. Retentive or explicit?
No, when it comes to writing things right and perfection and
You're a good
If I
group.
leave now, I might get home around